Hello. Today we are going to talk and start chapter 5. Excuse me. So, in chapter 4, we studied something called discrete probability distributions. And if you remember about discrete probability distributions, it meant we were counting something. So we had a finite number of outcomes. And depending on what that probability distribution was, like in binomial, you're counting the number of successes. In geometric, you're counting the number of trials to the first success, but you're counting something. Well, what if we have a continuous distribution? Because in a continuous distribution, we're not counting something. And we're going to talk about the most common continuous distribution that is of concern for statisticians, which is called the normal distribution. And that's basically the most important continuous probability distribution because a lot of things in real life are normally distributed. And you may have heard the term called a bell curve. And a bell curve is, when we talk about a bell curve, what they're really referring to is really a normal distribution is basically the bell curve. So it's useful in a lot of different scenarios. Talk about the normal distribution, and later we'll talk about how basically every single distribution is related to a normal distribution. So, with that being said, there are a few characteristics of a normal distribution that you should be aware of, and this first section of chapter 5 just introduces what a normal distribution is and how to find probabilities using the normal distribution, and then we'll apply this concept throughout chapter 5. So it's really important to really grasp what's going on in this first section, so that way you really understand what's going on in the next sections. Okay, so the graph of a normal distribution is called the normal curve, and it has the following properties. The mean, median, and mode are equal. And to kind of illustrate this to you, before I go through all the properties, this is your normal curve, so it has this bell shape, right? And I'll just make this the x-axis. And the mean, median, and mode are equal. Well, the mean, median, mode, because it's tallest in the middle, and it's symmetric, the mean, median, mode are the same. The second thing is that the normal curve is bell-shaped and symmetric about the mean, which is what I really already talked about. 3 is a really important one. The total area under the curve is 1. And this one's kind of interesting because if you think about the normal curve extends forever, never actually touches, gets really, really close, but never actually touches the x-axis, which is the fourth thing. The normal curve approaches but never touches the x-axis as it extends farther and farther away from the mean. But yet there is an area under this curve, and the area under the curve is 1. And that reason why that area is 1 is because this is a probability distribution. We're adding all of the area together, and we're getting 1. Very similar to a discrete probability distribution. When you add all the different cases together, all the probabilities together, you get 1. And the same works for continuous probability distributions. It's just now it's an area we're talking about because it's continuous. It's on an interval. And then the inflection points are at mu minus sigma and mu plus sigma. So to kind of show you where these are, if you go 1 standard deviation away from the mean, these are inflection points. And an inflection point is where basically the steepest point on a curve is. So if I imagine I'm in like a little car, or let's say I'm on a bike. I like the bike analogy more. So this is my bike. Okay, these are my handlebars. You know, I'm sitting on my bike. I'm pedaling. Yay, I'm pedaling up my bike. Okay, so I'm pedaling up my bike. Okay, and if you imagine you're on the bike, when you hit about this point right here, when we hit about this point, it's going to be hardest to pedal. But after I get over that point, it gets easier and easier and easier. And then likewise, when I go down the hill, I'm gaining the most speed when it's steepest, right? And then it levels off. Well, these steepest points are called inflection points. And it turns out that 1 standard deviation away from the mean, mu plus sigma and mu minus sigma, is where the inflection points are located. And then from there, you can kind of see where 2 sigma is away from the mean, and then 3 sigma. And so on. Okay, so those are some basic characteristics about the normal curve. I would definitely say the most important thing to remember is, as you're drawing it, the inflection points, that's 1 standard deviation away from the mean. And definitely the most important thing is what I start up here, which is the total area under the curve is 1, because we're going to utilize that in a little bit. So with that being said, there are many things that are normally distributed. For example, the heights of people are normally distributed. The return on investments is normally distributed over time, typically. Well, each of these normal distributions have a different curve because it has a different mean. Like, why would the mean height be the same mean as a return on an investment as the same mean as something else that's normally distributed? All these means and actually standard deviation of all those data sets are different. So what we do is we standardize the data. We have what's called the standard normal distribution. And the standard normal distribution is a specific normal distribution where the mean is in the middle, but we give it a number. And we give it an easy value to as a reference point, so we give it the value 0. Then 1 standard deviation, so remember my inflection point's about right here, so that's about 1 standard deviation, 2 standard deviations, 3 standard deviations, and we set my standard deviation equal to 1. So my mean is 0, and my standard deviation is equal to 1. And we'll do the same thing on the negative side, so my inflection point's about right there. And therefore, every value on the axis is 1 standard deviation away from the mean. So the number of standard deviations you have away from the mean, this is a specific name. You learned about this in chapter 2. This is called a z-score. And you can use z-scores to find probabilities under a standard normal curve. And remember, the formula to find z-score is x minus mu divided by the standard deviation. Now, we're not going to use this formula quite yet, but it is important to understand that you can use this formula to get a z-score in any data set, and then you can use the standard normal distribution to find the probabilities. So how do we actually find these probabilities? And this is really the main point of 5.1. It's very important to understand this, what I'm about to talk about here. Well, how do I find these probabilities? Well, what I can do is I can look at a table. And this table is uploaded to Canvas. You can also view it in the back of your book. If you're doing Math Excel problems, the table is often available for you to look at too. But I'm going to put this table up here, and this is basically the standard normal distribution table. So the table is actually 2 pages, and basically it tells you the area to the left of a z-score. There's, by the way, another table that exists. So if you ever like Google search standard normal distribution table, because there's a lot of them out there, you can just look up the table, look up standard normal distribution table. There's some areas that go away from the center 0 on either side, and it's only 1 page. Some people prefer that table, but I've always used the one that's the area to the left because it's a cumulative probability. And the standard normal distribution table always gives you the area to the left of a specific z-score. So for example, if I want to look up the z-score negative 2.75, negative 2.7, and then 5.05 is up here. So negative 2.75 is going to be, looks like this right here. So the area to the left of negative 2.75 is 0.0030 or 0.3%-ish. And that's what you do. You look it up. There's no way to really calculate it. You just have to look it up in the table. And remember, the table always gives you the area to the left. And if you go to the positive z-score side, the positive z-score page, these are larger areas because they're positive z-scores. So you have, once your z-score is positive, you have over half of the curve to your left. So for example, if you look up like 0.67, that is 0.7486 of the area to the left of that z-score. Okay, and remember, it's always the area to the left. I like to always bring up the wise philosopher Beyonce helped us when she said to the left, everything you own in the box to the left. And whether she knew it or not, she was talking about z-score tables. Okay, so let's look up and try to find these probabilities / areas. So we want to find the area to the left of the normal curve where the z-score is negative 0.99. So these are actually probabilities, so it's good to get in the habit of writing a probability statement. So we want to find the probability to the left is less than. So to the left is less than negative 0.99. And to find the probability that a z-score is to the left of negative 0.99, what we do is we go to our table, and we look up negative 0.99. Okay, and I'm going to have to zoom out a little bit here so I can see it. Okay, so negative 0.9 is right here, and then the second 9 is here, so negative 0.99 is 0.1611. So the area to the left is 0.1611. And that's it. We just look it up like that. Now, to kind of give you a visual here, and I suggest for all of these, at least at first, you draw a bell curve. So all we did is, if this is 0, negative 0.99 is about right here. And we looked up, we found that area. Okay. I'm going to have to write about it because I covered up my problem on the next one. Okay, let's go to the next one. Now the next one is a little bit different. It's to the right. So we want to find the probability that z is now, because it's to the right, it's greater than 1.06. Well, let me draw this out for you. This is 0, 1.06 is like here, and we want the area to the right. Well, the table only gives us the area to the left, but if you remember, there's a property of a normal curve. The total area is 1. So if I take 1 and I subtract the area to the left, I will get what's left over, which is the area to the right. And that's exactly what we're going to do. So I'm going to look up 1.06, which is going to be on the positive z-score table. 1.06 is 0.8554. And I'm subtracting that from 1. So my final answer is going to be 0.1446. Okay. So that's the area to the right of the z-score of 1.06. All right, so that's the area to the left, that's the area to the right. What if I have two z-scores, though? What if I want to find an area that's in between? So I want to find the probability that z is between negative 1.5 and 1.25. So that's this area, which I'm going to color in blue. Okay, so I want to find the area in between two z-scores. Well, to find the area in between two z-scores, remember, if you look up the area in the table, it'll give you the area to the left. So here's what we can do. If I look up the area to the left of 1.25, if I look up the area to the left of 1.25, that'll give me this blue area, but it will also give me, I'll use a different color here, this green area as well. So if I want to look up the area in between the two, I have to subtract this green area away from looking up the area of 1.25. So what I can do is I can look up the area of 1.25, and then I can subtract when I look up the area of negative 1.5, and that'll just give me the blue area. So once again, if I look up the area of 1.25, that'll give me the whole area under the curve. And then I'm going to subtract away the area to the left of negative 1.5, which will just give me the area of in between left over. So 1.25, when I subtract, or when I look it up, 1.25 is 0.8944. And I'm going to subtract negative 1.5. So negative, that's over here, negative 1.5. And it was just negative 1.5, so that's versus 0.0668. Yeah, 0.0668. Okay, yeah. So let's see. So that's 0.3. So that's 0.8. 276, I think. Okay. All right. So that's how you find the area in between two values. Okay. Now, the last one is on either side. So when we want to find the area to the left, so we want to find the area that the probability that z is less than negative 1.3, and we have to add the area to the right, z is greater than 1.92. So negative 1.3 is right here. 1.92 is right here. This is 1.92. This is negative 1.3. So we want to find these areas. Well, we can do something very similar. If I find the area in between, I can subtract that area from 1, and then I'll get the area left over on the sides. By the way, there's a couple ways to do this, but this is how I always like to do it. So if you figure out a way that you think works better, then that's fine. But this is how I like to do it. So I'm going to still find the area in between, which is the blue area. So I'm going to look up 1.92. So I'll put this in parentheses. I'm going to look up 1.92. Let's see, 1.92 is... I like to look at my headings here. 0.9726. So I'm going to write that down. So that's the area to the left of 1.92. So now I'm going to subtract the area to the left of negative 1.3. Look up negative 1.3. 0.0968. Yeah, 0.0968. If I can find my notes here. Gosh. 0.0968, and then I'm going to subtract that from 1. So let's see, 0.9726 minus 0.0968 is 0.1242. That's my final answer. Just realized I put 2 zeros here. Okay. And that is how you find the area under the normal curve. So these are the 4 main cases that there are. You can find the area to the left, which is easy. You just look in the table. To find the area To the right, you look in the table, but then subtract that from 1. To find the area in between, you subtract the 2, and to find an area on either side, you subtract the 2, and then subtract that quantity from 1. Okay? And that's basically it. It's very important, like I said, you get a grasp on this in the beginning. So I would advise do the 5.1 first after you watch this, and then actually move on to 5.2. Don't skip ahead, because basically every problem in 5.2 boils down to one of these. So it's very important you get something like this. A quick side note, and that is sometimes they'll ask you to find an area. Like, let's say I ask you to find an area to the, here, let's say, oops, I didn't want that. There we go. Okay, I just needed a little more room to write. Okay, let's say we find an area to the left of, I don't know, 1.255. Well, if I look up 1.255, this isn't in the table, right? Because the table only is accurate to 2 decimal places. So what you do is you look up the area 1.25, you look up the area 1.26, and then you average them. And this will only occur if the third decimal is a 5, because that is right in between 1.25 and 1.26. So to illustrate this, if I look up 1.25 and 1.26, 1.25 is 0.8944, and 1.26 is 0.8962. So 0.8944, 0.8962. Let me double check that that's right. Yeah. Okay. So the answer, if I wanted to find the area to the left of this, the answer is these added together divided by 2, because that's how you find the average, right? And that's what you would have to do to find that, which I believe would be 0.8953, I think. Okay. So just keep that in mind if you see one of these with 3 decimal places. I wanted to point that out. Okay, so that's it, and have a fun finding areas under the normal curve.